Hey guys, Sid here. It's been a while since I last uploaded, but I can assure you that I am back. While other demands can keep me from uploading consistently, I promise to do my best. Today we will be looking at complex numbers. These are often to signify an imaginary value, non-existent on the real number line. The number line is 0, 1, 2, 3, negative 1, negative 2, negative 3. Complex numbers do not exist on this number line. They are non-existent here, but present for the sake of mathematical expressions. Most commonly, it will be used to express negative square roots in the form of the letter I. Why are complex numbers necessary? To solve the equation x squared minus 4 equals 0, we get x squared equals 4 and x equals plus minus 2. We get an answer here. It's a clear answer. The answer can either be x equals 2 or x equals negative 2. Both will satisfy this. However, when we have the equation x squared plus 4 equals 0, and we are asked to solve this and find the value of x, and we move 4 to the other side, so x squared equals negative 4, x equals the plus minus square root of negative 4. Now, what you've been taught in school probably is that the square root of negative 4 is undefined. There is no answer to the square root of a negative number. This is undefined in the real number system because the square of any real number is positive. The square of negative 2 is 4. The square of negative 3 is 9. So the square of any real number on the number line is positive. So therefore a negative square root cannot have an answer. So we face so many difficulties when we see negative square roots. To allow it all to have a proper answer, to allow it all to be properly mathematically expressed, mathematicians invented an expanded number system. That can define any negative square root. That can define any negative square root. In complex numbers, let's dive into it directly. In complex numbers, there are a few essential equations to memorize on top of the concept itself. So as I mentioned before, the principal expression for complex numbers is the small I. This is the most popular and it's universally recognized. So this I, for the sake of complex expressions, is equal to the square root of negative 1. I equals the square root of negative 1. I square is equal to negative 1 times negative 1, both in a square root, which gives us negative 1. I cube is I square times I. So it's negative 1 times I, which is negative I. And our favorite, I to the power of 4, which is I square times I square, which is negative 1 times negative 1, which is 1. So these are the 4 different degrees of the complex number I. And it is very important to memorize all of this, because when we are looking at complex numbers and complex expressions and we want to convert them to the simplest possible extent, we need to know which degree of I is equal to what value on the real number line. So I, being the imaginary number, equals to all these values. So when we replace these values with I, we can express even a negative square root. So usually when we express complex expressions, complex numbers will be written in the form a plus bi. A plus bi. And in a plus bi, a is the real part. A is a number on the real number line. And b is the imaginary part. The coefficient of I is obviously the imaginary part. This is the part that ordinary mathematics cannot define. but combined it can create an expression that is universally recognized. So let's see the parts of complex numbers. So we have 3 plus 4i, and 3 plus 4i is a complex expression, and in 3 plus 4i, based on this, 3 is the real number on the number line, and 4i is the imaginary part. And we have expressions like this, but we also have something called a pure imaginary number, such as 7i. 7i does not have a real part, so we assume it's 0. 0 plus 7i is the proper complex expression. A real number such as -7, which is on the number line because this is an integer, this can be considered to have an imaginary part consisting of 0i, which we do not use in everyday life, but for the sake of mathematical expression, that's. So therefore, let's have a look at a variety of different questions and how we can apply complex numbers, how we can manipulate them. So just like ordinary algebraic expressions, we can manipulate complex numbers. So 2i square, 2i whole square. So this is a complex number to the power of 2. So just like we treat any ordinary algebraic expression, we square both the elements inside the bracket, so 4i square. And as I had introduced before to you, I square equals -1. So 4 times -1. We always try to replace the I with its real equivalent. So I square will be substituted with -1. So 4 times -1 will give -4. And when we have -2i square, it's -2 square times I square. -2 square is 4 and I square is -1. So it both gives the same answer of -4. Complex numbers can be added, subtracted, multiplied and divided. The only difference is that we have to understand that I square is -1 and that I is equal to the square root of -1. So therefore, if we use these equivalents, we have to give the final answer in the form a plus bi, which is absolutely important because all of the questions you will see in complex numbers will ask you to give the answer in the form a plus bi. So when we add expressions in complex form, so 3 plus 5i plus 4 minus 2i, for example, so we obviously, like we treat all algebraic expressions, we combine like terms. So 3 plus 4 is equal to 7 and 5i minus 2i is 3i. As simple as that. And we can even multiply 3 plus 5i times 4 minus 2i. So we expand. 3 times 4 is 12, 3 times -2 is -6i plus 20i minus 10i square. We combine the like terms, 12 plus 14i minus 10i square. So now I square is equal to -1. This is absolutely important. So I square can be substituted with -1. So 12 plus 14i minus 10 times -1. And this will give us the final answer, 12 plus 10 plus 14i, which is equal to 22 plus 14i. In the answer 22 plus 14i, 22 is the real number and 14i is imaginary. Hence a plus bi. This is how we manipulate ordinary complex expressions. But now let's look at something actually tricky, something that will put into use the equations that we are forced to memorize actually. Okay, we're gonna solve this question, and for that we have to revise what we learned first. Never forget this. I is equal to the square root of -1. I square is equal to -1. I cube is equal to -I, and I to the power of 4, our favorite, is equal to 1. Using this, we are going to solve this equation, I to the power of 23. And we have to present it in the simplest form possible. This is a very high power, and don't get scared by this. The first step is to break this down. So I to the power of 23 is I to the power of 22 times I. Okay, 22 plus 1, the law of exponents gives us 23. So now we have to break down I to the power of 22 into simpler forms. So since we have I square equals -1, we have to find a way to get I square inside here. So let's keep I square in the bracket and put this to the power of 11, because 2 times 11 gives us 22. And let's let I remain as I, okay? So now I square is obviously replaced with -1. So -1 to the power of 11 times I. 1 to the power of any number is 1 at the end of the day, and because this is a negative inside and the exponent is an odd number, so -1 to the power of 11, if you check your calculator, will be -1. And -1, I stays the same. We don't break this down usually to the square root of -1. So -1 times I gives us -I. That's the simplest form we can present this complex expression in. If we memorize these 4 principles in complex numbers, we can basically solve any complex expression. Okay, division of complex numbers. You see, division of complex numbers is much like rationalizing the denominator of a radical expression. For example, when we had in the past, when you were working with radicals, when you had 1 over square root of 2, to convert this to a proper expression, you didn't want the square root and the denominator. So you multiplied up and down by the square root of 2. And this automatically eliminated the radical in the denominator. So it becomes square root of 2 over 2. So the division of complex numbers is almost exactly the same. For that, we have to understand this term first. It's called the conjugate. For example, the conjugate of 4 plus 3i is 4 minus 3i. The sign in between the real and imaginary number is switched from positive to negative. And it's the same from negative to positive. So to rationalize a complex expression, we have to multiply top and bottom with the conjugate expression of the denominator. So for example, when we have the expression 3 plus 5i over 1 minus 2i, first we have to identify the conjugate, the complex conjugate of 1 minus 2i. Complex conjugate of 1 minus 2i is 1 plus 2i. The sign in between is switched to a positive. Therefore, when we multiply 1 plus 2i to the numerator and the denominator, we get 3 plus 5i multiplied by 1 plus 2i over 1 plus 2i times 1 minus 2i. At the top, we do regular expansion to get 3 plus 6i plus 5i plus 10i squared. For the denominator, we apply this. A plus b times a minus b is equal to a squared minus b squared. So 1 times 1 is 1, 2i times negative 2i is negative 4i squared. And again, we're going to apply the rule of I squared being equal to -1 into this to simplify this to the simplest possible to get the simplest possible expression. So we combine the like terms. So 3 plus 11i plus 10i squared over 1 minus 4i squared. Now we have this. We think that this is the simplest possible way to present this answer, but we can go even further with our understanding of complex and real equivalence. So 3 plus 11i plus 10i squared over 1 minus 4i squared can easily be converted to eliminate the any I to any degree. So I square equals negative 1, which basically means 3 plus 11I plus 10 times negative 1 over 1 minus 4 times negative 1, because I square is equal to negative 1. So that essentially makes the numerator a negative 7 plus 11I over 1 plus 4, which is 5. So that is the simplest possible way to present this answer. As you can see, after we rationalize, after we divide the numerator and the denominator in a complex expression, we can get rid of any complex number in the denominator. This goes the same for any type of question where there is a complex number in both the numerator and the denominator. Let's have a look at another one. So let's say we have the expression 7 plus 3i over 4i. Okay? Now, to get rid of any possible complex expression in the denominator, we have to multiply the top and bottom by the conjugate of the denominator. The conjugate of 0 plus 4i is 0 minus 4i. So we multiply the top and bottom by the negative conjugate. So 7 plus 3i multiplied by negative 4i, 4i times negative 4i, multiplied to negative 28i minus 12i square over negative 16i square. So negative 28i, we replace the I square with negative 1 over negative 16 times negative 1. So negative 28i plus 12 over 16. This is the simplest possible way that we can express this, where there isn't a complex expression in the denominator. So this is the final answer. And to express this in the form a plus bi, we break it down into two different fractions. So 12 over 16 minus 28 over 16i. It's in the same form as a plus bi. This is the real part, this is the imaginary part. And that is basically how you deal with complex numbers. Now, at the start of this video, I was talking about the purpose of complex numbers. Mathematicians invented this to deal with negative square roots, expressions that could not normally be expressed in the real number line. But I haven't gotten to that yet. The square root of negative r, okay, where r is a real number, is equal to I root r. And the I, as we remember it from the start, I is equal to the square root of negative 1. So fundamentally, from the real number, we are splitting the negative part of the real number, because a negative number multiplied by a positive number gives a negative number. So we are essentially removing the negative part. The square root of any negative integer is equal to the I to the root of that positive integer. For example, the square root of negative 5, which will be undefined in the real number line, is actually equal to I root 5. Because the I is root negative 1. So what we are left with inside the square root is essentially 5. And the square root of negative 7 is obviously I root 7. So the I represents the negative part of the integer, and we bring it outside. One important thing to remember when we're writing complex expressions, since we are often dealing with square roots, it's important to remember that the I should never be at the end, should never be, to write I root 7, we can never write it as root 7i. Because it is often misinterpreted over here, because sometimes your square root line, your square root can extend a bit more, and the examiner or your teacher will be unsure of whether this I is part of the square root or is outside the square root. So because to deal with the misinterpretation, we often put it at the start, because In normal expressions, we write 7x. 7 is the coefficient, x is the expression. We don't write x7. But in this special case, because of square roots, we have to write it like this. Now that we understand the principle of negative square roots, let's try a question. The square root of negative 25. First step, convert this to a complex expression equals I root 25. We bring the negative outside and we replace it with I. So I root 25. Root 25 is, as we all know, is equal to 5. So I root 5, I times 5. I times 5 is 5i. Now that the square root is gone, we can put the I at the back of the expression, because it won't be open to any more misinterpretation. Okay, please don't write I5, that's a processor. And negative 3 times negative 12. First step, convert both of this to complex form. So I root 3 times I root 12. I times I is I square. Root 3 times root 12 is root 36. By the law of complex expression, root 36 is 6. I square is negative 1, as we know from the start. We have to remember that I square is negative 1. So I square is negative 1, so 6 times negative 1 is equal to negative 6. So that is how we express complex expressions in negative square roots. So one thing to remember is that special care must be taken in performing calculations that involve square roots of negative numbers. We have learnt in the topic exponents times and radicals that the square root of a multiplied by the square root of b is the square root of ab. But what we may not know is that this law only applies when a and b are positive numbers. If both of these are negative numbers, this will not work. For example, the square root of negative 2 multiplied by the square root of negative 3 does not equal to the square root of negative 2 times negative 3. This is not the case. Therefore, when dealing with complex expressions, make it the rule of law that we have to convert this to a complex expression in the form of I, so we can deal with it as an algebraic expression rather than seeing it as a number. So let's have a look at this. Let's have a look at that same one. So let's have a look at negative root 2. The square root of negative 2 times the square root of negative 3. First step, convert both of this to complex form. If both of this is converted to complex form, it's I root 2 multiplied by I root 3. So the root and the root can be combined like expressions, and the I and the I form the I square. So the I square root 6. I square is negative 1, so negative root 6. It's a much simpler way to express this, and there's no room for confusion over here. So the rule of law when using negative square roots, convert them to complex numbers first. Do not try to manipulate them and make it in such a way that it's easier to substitute. Substitute, convert, and treat them like algebraic expressions. Now, to practice what we've done, let's try one last question that I think will sum up this entire topic. So the square root of negative 7 multiplied by the square root of negative 49, both of these are negative square roots, over the square root of 28. First rule of law, the first step in answering, convert to complex form. So the square root of negative 7 will be I root 7 multiplied by I root 49 over the square root of 28. Okay, once we have done that, let's break this down. I root 7 stays I root 7. The square root of 49 is 7, so this is multiplied by 7i. Bring the I to the back because there is no more room for confusion, and the denominator is the square root of 28. So there are problems over here. In the denominator, we have the square root of negative 28, and we should not have radicals in the denominator. So the ordinary way to rationalize this would be multiply the numerator and the denominator by the square root of 28. But here we're going to be using a different method. Let's apply what we know from radicals. Now that we have everything is a positive square root, we can treat it as normal maths from now on. So I root 7 times 7i will be equal to 7i square root 7 over the square root of 28. The square root of 28 can be split into 7 times 4, which we know from radicals. So 7i square root 7 over root 7 times root 4. If we cut the root 7 at the top and the bottom, we have 7i square over the square root of 4. And 7i square to the square root denominator is the square root of 4. We have 7i square over 2. That's the final answer. But we can simplify this further. This is the final answer in complex form, but to give it in real number format, we have to convert I square to negative 1, which gives us negative 7 over 2. Negative 7 over 2 or negative 3.5 is the final answer to this. This is the easiest way to convert a negative square root into a real number, and this is how we often deal with negative expressions. While negative square roots in complex numbers aren't always applicable in every question, this certainly makes answering questions much easier. For example, when we apply the quadratic formula negative b plus minus square root of b square minus 4ac over 2a, the entire solution is not possible if the square root of b square minus 4ac, if the square root contains a negative number. But when we use complex numbers, there will always be a solution. That is important to remember.